Today we're going to talk about inverses of matrices. You may have noticed that we've already talked about scalar multiplication, matrix addition, matrix subtraction, matrix multiplication. We haven't mentioned division. You might wonder, can you divide matrices? Well, we're really not going to talk about division, but we are going to talk about multiplying a matrix by its inverse. Multiplying by its inverse would be a type of division. Remember, to multiply fractions, you multiply the dividend by the inverse of the divisor. So to divide matrix A by matrix B, I would multiply A by the inverse of B. So we need to talk about inverses. Matrices that have inverses are called invertible. Matrices that have no inverses are called singular. The idea of singular matrices, invertible matrices, will be used throughout the course as well. So in these first few tapes, we are really introducing ideas that you will use more and more and more as we continue through the series. Now, all of today's work requires that we start with a square matrix. So a square matrix A is invertible if there exists a matrix B such that A times B is equal to B times A is equal to the identity matrix. So it's invertible if I can find another matrix B so that if I multiply A by B or B by A, I get the identity matrix. The matrix B is called the inverse of A. So the matrix B is called the inverse of A and is denoted by A with a -1. So if you see A with a -1 superscript, you read it A inverse. So then combining this statement with this notation, if A has, well, first of all, singular. If A has no inverse, then A is singular. So if A has no inverse, then A is singular. Now, back if I combine AB is equal to BA is equal to I with the notation for the inverse, then I have A times A inverse is equal to A inverse times A is equal to the identity matrix. Now, to verify that two matrices are inverses, all you need to do is to multiply them together and show that you get the identity matrix. I'm not going to do that at this time. I'm going into the procedure for finding the inverse of the matrix 1, -1, 2, 3. Well, to find the inverse, I'd want A times A inverse is equal to the identity. So that's what I'm going to write now. So say this is going to be the inverse, if it exists. So we would have A times A inverse is equal to the identity matrix. Of course, this is the identity matrix. Well, we know that A is 1, -1, 2, 3. I'm looking for A inverse, so I need to know the elements A, B, C, and D so that A times A inverse is the identity matrix. I'm going to multiply these. A times A inverse, that would be A minus C, B minus D, 2A plus 3C, 2B plus 3D. So that's doing the multiplication. So if I multiply a 2 by 2 matrix by a 2 by 2, I'll get a 2 by 2. So I have a 2 by 2 matrix. And the identity is 1, 0, 0, 1. Two matrices are equal if and only if their components are equal. So I get A minus C is equal to 1. B minus D is equal to 0. 2A plus 3C is equal to 0. 2B plus 3D is equal to 1. So I get, really I have a 4 by 4 system. I have 4 equations and I have 4 variables. And I can solve the 4 by 4 system, or I could solve the 2 by 2 systems, because notice that this system doesn't involve B or D. This system doesn't involve A or C. So finding A, B, C, D is just a case of solving these systems. Well, to solve the system, here I can multiply by 3 to eliminate the C's. So I have 3A minus 3C is equal to 3. 2A plus 3C is equal to 0. I have 5A is equal to 3, where I get that A is 3/5. Now going back, A minus C is 1, so A minus 3/5 is 1. So that means A must be 8/5. 8/5 minus 3/5 would be 5/5, which is 1. I'm sorry, that would be C. C must be 8/5. No, I'm getting backward. No, I was trying to do it in my head. Let's just write it out. I have A minus C is equal to 1. A is 3/5 minus C is equal to 1. So 3/5 minus 1 is equal to C. So a negative 2/5 is equal to C. So then A, 3/5, subtract a negative 2/5 is 1. So we have A is 3/5, C is a negative 2/5. Now we want to solve this system, and I can multiply by 3 again to eliminate the D. So I have 3B minus 3D is equal to 0. I have 2B plus 3D is equal to 1. I add, I get 5B is equal to 1. B is 1/5. Going back, I see here that B is the same as D, so D is also 1/5. So that means A inverse is going to be 3/5 1/5, a negative 2/5, and 1/5. How do I know if I have the right answer? Well, if the answer is correct, then that means I'm going to have A times A inverse is the identity matrix. Well, let's check to see if that's the case. A was 1, negative 1, 2, 3. A inverse is 3/5, negative 2/5, 1/5, 1/5. If I multiply, that would be 3/5 plus 2/5, which is 5/5, which is 1. That's 1/5 minus 1/5, which is 0. 6/5 minus 6/5 is 0. 2/5 plus 3/5 is 1. So I know that this one must be the inverse. Because if I multiply A times this matrix, I get the identity. Therefore, this matrix must be the inverse. You're probably saying, is there a better way to find the inverse? Well, there's really not. But what I can do, I can solve the two equations at the same time and save a step or two. What I can do, I can take this system, since we have the same coefficients for both 2 by 2 systems, 1, -1, 2, 3, and that will always be the case. I can take it and solve them simultaneously by taking the coefficient matrix 1, -1, 2, 3 and joining it to the identity matrix 1, 0, 0, 1. So I'll just give you the notes. The two systems can be solved simultaneously by adjoining the identity matrix to the coefficient matrix. So I'm going to solve them both at the same time. Remember, if you think back, what did I do to start with both cases? I multiplied by 3, then added and solved. What I'm going to do to solve them simultaneously is to create the row reduced echelon form by making sure that the main diagonal is 1 and all the others are 0. Well, this time I'm going to multiply row 1 by -2, add to row 2. So I have 1, -1, 1, 0. And I'm going to multiply row 1 by -2 and add to row 2. -2 times 1 is -2, plus 2 is 0. -2 times -1 is 2. 2 plus 3 is 5. -2 times 1 is -2, plus 0 is -2. -2 times 0 is 0. 0 plus 0 is 0 plus 1 is 1. I'm going to multiply row 2 by 1/5. Now I get 1, -1, 1, 0. 0, 1, -2/5, 1/5. Now I'm going to add row 2 to row 1 because I want to have a 0 here. 0 plus 1 is 1. 1 plus a -1 is 0. A -2/5 plus 1 is 3/5. 1/5 plus 0 is 1/5. And of course I'm going to leave row 2 the same. So solving them simultaneously, I can see that A is 3/5. Well, by solving them simultaneously and creating the identity matrix on the left, I have the inverse on the right. So the inverse matrix is 3/5, 1/5, -2/5, 1/5, which is the same as we got before, just a little bit faster. Let's look at another example. Find the inverse of 1, -1, 0, 3, 6, 2, 0, 4, 1. create the matrix 1, negative 1, 0, 3, 6, 2, 0, 4, 1. And we'll have the identity on this side just like before. In other words, I'm going to solve a 3 by 3 system simultaneously. And if you set it up as I did the last example, you'll see the same thing happens. This is what you can do to solve the system. Put the coefficient matrix over on the left, put the identity on the right, and I'm going to use my row operations to create the identity matrix on the left. The matrix on the right will be the inverse. Well, my first step is to multiply row 1 by negative 3 and add to row 2. So I'll leave the 1, negative 1, 0, 1, 0, 0. Negative 3 times 1 is negative 3, plus 3 is 0. A negative 3 times negative 1 is 3. 3 plus 6 is 9. And negative 3 times 0 is 0. 0 plus 2 is 2. And negative 3 times 1 is negative 3, plus 0 is negative 3. 0 plus 1 is 1. 0 plus 0 is 0. Because when I multiply 0 by negative 3, I just get 0. And I'm going to leave the bottom row. So column 1 is okay. Now I'm going to multiply row 2 by 1/9. Be 1, negative 1, 0, 1, 0, 0, 0, 1, 2/9, and negative 1/3, 1/9, and 0, 0, 4, 1, 0, 0, 1. Now I'm going to add rows. I'm going to add row 2. I'm going to do two things at once. I'm going to add row 2 to row 1, multiply row 2 by negative 4, add to row 3. So row 2 won't change. It's going to be 0, 1, 2/9, negative 1/3, 1/9, and 0. Now I'm going to add row 2 to row 1. 0 plus 1 is 1. 1 plus negative 1 is 0. 2/9 plus 0 is 2/9. A negative 1/3 plus 1 is 2/3. 1/9 plus 0 is 1/9. 0 plus 0 is 0. Now we're going to multiply row 2 by negative 4 and add to row 3. Negative 4 times 0 is 0. 0 plus 0 is 0. Negative 4 times 1 is negative 4, plus 4 is 0. That would be a negative 4 times, be negative 8/9 plus 1 would be 1/9. That would be a positive 4/3 plus 0 is 4/3. That would be a negative 4/9 plus 0 is negative 4/9. 0 plus 1 is 1. Now I need to multiply row 3 by 9. 0, see, be 1, 0, 2/9, 2/3, 1/9, 0, 0, 1, 2/9, negative 1/3, 1/9, 0. Okay, we're multiplying by 9. 9 times 0 is 0. 9 times 0 is 0. 9 times 1/9 is 1. 9 times 4/3 is 12. 9 times negative 4/9 is negative 4. 9 times 1 is 9. Now I'm going to multiply row 3 by a negative 2/9 and add to row 1 and row 2, because I'm trying to create zeros here. So I'll have 0, 0, 1, 12, negative 4, 9. Okay. 0 times the negative 2/9 is 0, plus 0 is 0. That'll be 0. This will still be 1 and 0 because I'm just multiplying by 0. Now negative 2/9 times 1 is negative 2/9, so I add these two, I get the zeros. Okay, now I need to multiply a negative 2/9 times 12. A negative 2/9, so I'm multiplying negative 2/9 times 12 and adding it to a negative 1/3. So we have a negative 2/9 times 12. I'm adding it to a negative 1/3. Then I'm adding it to 2/3. So reducing here, 3 going to 9 3 times, 3 goes into 12 4 times. So that's going to give me a negative 8/3 minus 1/3, which is negative 8 minus 1 is negative 9/3, which is a negative 3. So we have negative 3. Now I'm going to add the negative 8/3 to 2/3. So negative 8/3 plus 2/3 is negative 6/3. Negative 6/3 is negative 2. Okay, so now we're multiplying the negative 2/9 times the negative 4. So negative 2/9 times negative 4 is a positive 8/9. I'm going to add 8/9 plus 1/9 is 9/9, which is 1. That'll be 1. Now I'm multiplying by negative 2/9 times 9 is negative 2. Negative 2 plus 0 is negative 2, negative 2. So my inverse is going to be negative 2, 1, negative 2, negative 3, 1, negative 2, 12, negative 4, 9. Now you can check my work by taking A and multiplying it by A inverse. And I don't really guarantee it. I'm just going through and showing you the process. So you may have caught a mistake. If you do, come by the office and tell me, and I'll give you a couple points. If one cannot solve the systems to get a unique answer, then the matrix is singular. So when you're trying to transform A into the identity to create the identity on the left side here, If you come out with all zeros, then that means you can't do it. That means the matrix is singular. So in the process of trying to get row echelon form, if you end up with a whole row of zeros on your left part of your matrix, then that's the indication that you can't do it. So the matrix is singular. It doesn't have an inverse. This property offers no particular advantage to what we're going to be doing now, but it's very important to what we're going to be doing later. One can use inverses to solve systems of equations. Let's consider you have the matrix equation AX is equal to B. So here's your coefficient matrix. Here's your solution matrix, and here's your set of constants. Then if I multiply both sides by A inverse, I have A inverse times AX is equal to A inverse B. Using the properties of matrices, I can regroup and put A and A inverse together. And I know that A inverse times A is the identity matrix. So I get I times X is equal to A inverse B. And of course the identity matrix times X is just X. So the solution matrix becomes A inverse times B. So as I said, the method offers no advantages for by hand solutions. It is good for computer solutions, but my main reason of giving it to you now is we will be using it to find the solution set, the solution space for sets of vectors later on. So we'll be using this property a great deal. I will illustrate it by using derive to solve a system. Use derive in the inverse method to solve the system of equations 2x minus 3y plus 4z is equal to negative 10. X plus y minus 5z is equal to 2. 7x minus 3y plus z is equal to negative 8. Well, first I'm going to write it in the form AX is equal to B. Coefficient matrix times solution matrix is equal to the constants. Well, if I write it in that form, the A becomes the coefficient matrix, so it's going to be 2, negative 3, 4, 1, 1, negative 5, 7, negative 3, 1. Here's your coefficient matrix A. Here's your variable matrix or your solution matrix X, Y, and Z, and here are your constants, negative 10, 2, and negative 8. So this is the form AX is equal to B. Well, we know then that the X matrix is A inverse B. So we go to derive. And author A, the coefficient matrix, 2, negative 3, 4, 1, 1, negative 5, 7, negative 3, 1. That's just your coefficient matrix. So this is matrix A. Here is matrix B. Well, I know that X is A inverse times B. So I have derive, do, A inverse times B. And this is how you get A inverse. I mean, you just type it. If number 1, expression 1 is A, then you do number 1 raised to the negative 1 power will raise to, that's how you can do A inverse, just like we've done inverses in other courses. So A inverse times, remember you used the period to get this, times B, and have it simplify, and you get that X is 17/20, B is 40, or Y is 49/10, and Z is 3/4. This is X, Y, and Z. We got it by doing A inverse times B.